Hi everyone, my name is Uganda Matthias Joseph, a member of Group 23 Final Project, and this is our project, Graph-Based Large Acoustic Reasoning Models for Patient Target Sound Extraction and Respiratory Monitoring in Resource Constrained Words. So the keywords include large acoustic models, which are deep learning models trained on massive amounts of audio data to understand, represent, reason over sound and audio signals. Then we also have graph neural networks, like you can see down here, which are deep learning models designed to learn and structure data as graphs with nodes and edges. So the nodes are the entities on which the data is designed, such as patients, and the edges is the relationship between the patients. So acoustic similarity can be a relationship. Then target sound extraction, which is a signal processing and deep learning technique that isolates a specific sound of interest for a mixture of overlapping sounds. Then patient monitoring is a technique of monitoring multiple patients within the same ward. Say we can have tuberculosis, asthma, and COPD patients residing within the same ward, and we are monitoring them at the same time. Then you have explainable AI, which refers to method technique that makes decision and prediction of AI systems understandable to humans. And then we also have knowledge distillation, which is a model compression technique where a small efficient model learns to mimic a large, more powerful model. When you look at the health sector of Uganda, you will see that most hospitals cannot afford specialized medical equipment that can monitor each patient who has a breathing difficulty. So most of the time, such patients are monitored by nurses and doctors within intervals, which risks the lives of the patients. This project is designed to monitor multiple patients at the same time within the same ward, and then send alerts to the nurses and doctors for a situation whereby a patient is under distress. This can help to reduce response time and also the manpower, and also save the cost on buying medical equipment that are very expensive and most hospitals cannot afford. So some of the papers we were able to review, we had real-time target sound extraction using waveformer, which proposes a transformer-based real-time target sound extraction model capable of isolating sound sources in overlapping mixtures. Yeah, so it was tested on a single channel audio mixture, which limits its generalization in real world. And then we also had a graph-based based audio classification using pre-trained models and graph neural networks, which proposes a novel approach for environmental sound classification by representing audio as graphs. Then we had enhanced respiratory sound classification using deep learning and multi-channel cancellation, which proposes an advanced deep learning framework for classifying respiratory sound by integrating multiple channels acoustically signals with more frequency capsule coefficient. Then improving respiratory sound classification with architecture agnostic noise distribution provides a comprehensive overview for evolving field of noise distribution. So all these papers can be able to help us contribute on the project that we are going to do, and also look at the limitations that we are facing and see where we can improve them and come up with a better system.
My name is Manja Janet, and I'll be taking you through the problem statement for the GLAM project. So let's start with the domain application problem. In Ugandan hospitals or healthcare wards, they're limited specialized medical equipment, and this is due to their high cost. They're expensive to purchase. There's absence of multi-patient monitoring tools, since each patient has to have their own tool to monitor them. So there's no tool that can monitor multiple patients at the same time. So we also have limited medical personnel in the wards, the hospitals, that can attend to patients in case of emergencies. So when we come to the computational problem, the problem is the processing of noisy multi-patient data. These are the audios, the different sounds. And this may include things like source separation, because we don't isolate these sounds and pick out the important ones, which are the breathing patterns of the patients. So extracting the features from these sounds and then attributing different sounds to each patient, that this sound came from this patient. They may need graph-based reasoning to detect the anomalies in these sounds, like what could be wrong with the patient at a particular time. Our research questions, some of the questions we come up with were, how can real-time anomaly detection algorithms be adapted to identify abnormal respiratory patterns when we are having continuous hospital monitoring? What architectures are most effective for detecting deviations in the breathing patterns? Also, how can large acoustic models be easily deployed since they're very large? So some of the objectives we drew from our questions: want to derive respiratory patterns using graph-based reasoning. This would help us know the relationships between different patients depending on their respiratory sounds. To fine-tune a large acoustic model, since some of them that are existing are trained on other forms of data, but we want to train them on respiratory data. I want to distill knowledge into a lightweight acoustic model such that it can be easily deployed on a resource-constrained device and that can be used by different hospitals. Then to ensure continuous learning, this will help us improve the model and make it more robust. So Our research contributions, we are providing a graph-based modeling that captures complex temporal and physiological breathing patterns, since graph-based reasoning is just going to help model those relationships between different patterns and make the model at least more robust. We want to use large acoustic models to train on limited respiratory data. And then a lightweight edge deployment, we want to use knowledge distillation here for the lightweight to produce a lightweight model. Overall, our output would be an IoT application, and an IoT device that is going to monitor multiple patients in a ward.
We have two datasets. The first dataset was gotten from the International Conference on the Biomedical and Health Informatics, which was specifically gotten from the original website, and the other was gotten from Hugging Face. The one of Hugging Face, it had these labels that you can see here in the table. Like it had pneumonia, COPD, potential disease, then URTI, bronchitis and bronchitis, LRTI, then asthma. These are the distributions of those labels. Then the dataset from the official website, it had content of 5.5 hours of audio recording from specifically 126 patients. So we are determining from 126 patients, we are able to determine the top chest, the anterior left, anterior right, as you can see here in the image, then the lower left, lower right, then the posterior right and posterior left. Taking you through. So we carried out data cleaning, which was the exploratory data analysis. Then we are able to statistics of different, like the outliers, and then the heat maps, box outliers, spectral. Okay, I mean the means, the accuracy, the test accuracy, the training accuracy. Okay, it is going to be used. So from the official website, then to the data set from the Hugging Face, we are able to determine using the respiratory conditions of the MFCC one. Then this is the outliers, box outliers. Then this one is the like label distribution to see how, like, which one performed so highly, like which disease was highly captured. Then the different outliers, like how it is distributed.
I'm going to take you through the methodology, which starts with collecting sound from the patients. Once you collect the sound from the patients, our microphones will be having a signal conditioning, so a noise suppression and bandpass filters in order to receive the sound more clearly. Then from these microphones that will be placed strategically in the room, we shall do a source separation of these microphones in order to receive the sound from each. From these separated sounds, we shall do a feature extraction. This feature extraction will have acoustic analysis, a breathing detection, a biomarker extraction for each of the patients that are in the room, and we shall mark respiratory rate and also pick up on advantageous sounds. From these that we have created, we shall have a patient attribution from what we've had from the extracted features. Now, this patient attribution has an embedded best matching and a stream assignment for the patients that are existing in the ward. We shall do reasoning and analysis on the audio that we shall be having, whereby each patient that is existing in the ward can be monitored and the system learns to know the features, the unique characteristics of that patient and for the different respiratory diseases that exist. Now from this, we shall be able to identify anomalies. We shall have a rule-based detection using RL thresholds, pattern deviations, and a machine learning-based detection using temporal anomaly detection. So whatever anomalies that will be detected from the patients will be alerted to the interface, showing the patient ID, the location, and the severity of what this patient has. I'm going to take you through the implementation, which starts with collecting sound from the ceiling microphones, and then it will be wired to the microprocessor, which is our Raspberry Pi. It will perform audio synchronization, noise reduction, feature extraction. It will perform all these tasks that you see here, and keep these on a local buffer or on a temporary storage. This information will be sent to the nurse's workstation in real time. So this nurse's workstation will be connected to the cloud server via a secure access. This cloud server will have models, and these models will train on the audio that was received from the ward. The model training and distillation will be performed on the cloud server, as well as the sound storage from the different wards. So from the storage that has been collected from these patients, we shall have analytics and reports being made from them. And these reports will be used to make long-time assessments on the patients. And since they are connected to the Raspberry Pi, they'll always come back to the nurse's workstation. I'm going to take you through the models we trained, starting with our two-stage hybrid model, which uses an acoustic model, the YAMNet feature extractor, and tree ensemble models to perform classification. So the first thing we did was to perform categorization of our audio set into COPD, the largest class, the healthy, and the other, being the other respiratory diseases that exist. So the first thing we did was, once this three-class separation is done, we preprocess and resample the audios to 16 Hz, feed it into the YAMNet extractor, then it performs a multi-strategy pooling, which is later then placed into a feature vector. This feature vector then distributes this audio equally to the models that we had, the XGBoost, the random forest, and the gradient boosting. From this, the best of them is selected, which was the XGBoost, and is used to perform classification. So later on, we decided to train another model, which was a large acoustic reasoning model, which is designed for multi-patient monitoring. Instead of treating the audio clips as one entity, the model organizes the recordings into temporal sequences of 3 consecutive samples per patient so as to capture the breathing. What we did was to apply multi-patient input processing for the audios that we had. Then we did multimodal feature extraction. From these patients, we performed a temporal graphical neural network that used multi-patient attention and temporal sequence processing and feature projection. The multitask output heads were received, and with this, we performed a simple test to see how this model was performing best, having the confidence scores, the severity regressor, as well as a diagnosis classifier for the 6 classes of the audio set that we had. So yes, the last model was the optimized convolutional neural network, which was specifically designed to address severe class imbalance in our respiratory dataset. So it employs a streamlined architecture that directly processes the raw audio forms into millispectrograms before applying hierarchical feature extraction to the convolutional layers. So when you take a look at our diagram, you see that we do intelligent data splitting of our dataset and do class-aware augmentation, whereby we have the moderate augmentation and the aggressive augmentation, depending on how much these diagnosed audios are in our dataset. So we perform audio preprocessing, and then we do millispectrogram conversion here. So from this, we shall have the severe class imbalance strategies for those that are underrepresented, like asthma. So with this, we shall feed our severe classes into the training pipeline, into our convolutional neural network, as well as our classification head with A, and as well as our classification head. So these classes that are underrepresented are kept rather than they are left as markers so that the model learns from those in case it comes across other patients with similar breathing patterns as well. The heat maps display the performance for each model, and each diagonal represents the correct predictions for each model. And as you can see, this here had the best performance, the XG model. The LARM model, we are going to have to put it aside because it had data splitting issues. Rather than training on all the 6 classes of the diagnoses that were there, it used only 3. So its results are not comparable to the OCNN and the XGBoost. So this table summarizes the results that we had from our models 1, 2, and 3. Our evaluation will be based on the dominant class and its ability to perform well on the other minority class. So as you see, the majority class, which is COPD, the most stable results come from model 1, but when it comes to model 3, you realize that the difference between the recall and the precision is much wider. And when it comes to the minority class, you see that model 1 has a limited coverage, but it's better than model 2 or model 3.
The limitations we had, first of all, the model, the LARM, the large acoustic model, showed some promises, but first implementation challenges. While innovative in multiple patient relationships modeling, it suffered from the data splitting issues and architecture complexity. CNN model, because of the investigations that computes, then the conclusion, the simplified anatomy, the 3-class taxonomy was strategically effective, collapsing rare conditions. Then the OCNN revealed limits of technical solutions to the data imbalance, but it failed on condition with lower than 10% 10 samples. Then taking you to the next steps, like what are our future targets? Refining our model 1, given its strong performance, that was explained by my colleague Kathy. Then addressing the severe class imbalance, because there was a lot of class imbalances for the improved detection. Then develop and a validation of the multiple patient pipelines through using simulations, creating scripts to calculate the SDR for source separation, implementing the patient tracking metrics, and then the system. Then acknowledgement, first and foremost, we thank the good Lord, the Almighty, who blessed us and enabled us to identify and pursue this research idea successfully. Then we express our heartfelt gratitude to our supervisor, Dr. Marvin Galiwango, for his unwavering dedications, motivation, support, and guidance throughout the preparation of this proposal. We also extend our appreciations to our class, the computer science, for their support, the constructive feedback and encouragement.